So we just saw that there's a strong similarity between the structure of solutions to an nth-order linear differential equation and the structure of the solutions to a matrix equation. In both cases, the solutions form vector spaces. So in both cases, we're talking about linear algebra problems, at least from a certain point of view. What we're going to find now is that there's another relationship between these kinds of things. Here we go. Suppose we have a nth order linear differential equation. Note that this is not homogeneous. And suppose that I have a solution, and we're going to choose one and stick with it. So I'm going to call this y sub p, p for particular. This is a particular solution. Pick one, stick with it. Okay. Now suppose furthermore that you have a fundamental set of solutions to this associated homogeneous linear differential equation. By associated, I mean note that the left-hand side is exactly the same. The big difference is that the right-hand side is now 0. Of course, it's only for homogeneous linear differential equations that we know that the solutions form a vector space. Okay, so with these together, we can actually write down all of the solutions to this non-homogeneous linear differential equation. All of these solutions take the form of whatever that particular solution was that you picked, plus the complete collection of all homogeneous solutions. So keep in mind we had a fundamental set of solutions, and all of the homogeneous solutions are linear combinations of that fundamental set. Okay, so you see the similarity, I'm sure, between this theorem and a theorem that we saw concerning matrix equations, and that is the complete collection of all solutions is pick any particular solution and add to it the complete collection of homogeneous solutions. Okay, so let's see a proof of this result. We'll start by assuming that we have some function of this form. Let's plug it in and see what L turns out to be for this function. Well, by linearity, we have this. By assumption, L of y1 is 0, because we're assuming that y1 is a homogeneous solution, so that's 0. Likewise, these terms are all 0, so those all go away. By assumption, y sub p is our particular solution to that equation. That means that that's equal to that. And altogether, we find that L of y is g of x. And so therefore, everything of this form is a solution. Okay. Now we need to go the other way. Let's suppose that we have a solution, and let's show that it has the desired form. Well, so assuming that this is a solution, keep in mind that what that means is that L of y is equal to g of x. Don't forget that by assumption yp is a solution to that non-homogeneous equation, so L of yp is also g of x. And therefore, by linearity, y minus yp is a homogeneous solution. Now, this is very useful observation. In particular, if y minus yp is a homogeneous solution, recall that all homogeneous solutions are linear combinations of the fundamental set. And so therefore we can write that. And as required, solving for y, we have that it's the particular solution plus a homogeneous solution as desired. Okay. Now, so this theorem is very similar to this theorem that we saw back in Chapter 1. The theorem that we saw back in Chapter 1 is a little bit anticlimactic because, well, we already had a method for solving systems of equations, even non-homogeneous ones, which is a row reduction. And so the particular and homogeneous solution theorem didn't seem to buy us much. What we're going to find in this context, though, is that finding these homogeneous solutions is going to turn out to be relatively easy. Now, there's a whole discussion, and it's not trivial, but it's something that we can do. We are subsequently going to find that finding a single solution to the non-homogeneous equation is also something that we can do. But finding one is hard enough. So this is barely all we can do in terms of particular solutions. This is something that we can do for homogeneous solutions. And so we have, therefore, a way to find all of the solutions to these differential equations. So we're going to rely on this theorem. We don't have other alternatives. The method that we use to find this particular solution, it's only going to yield one solution, usually. So we need this connection relating the homogeneous solutions in order to find all of the solutions. Okay, this is a big theorem. And let's see an example. Let's look at this differential equation here. Now, at a glance, it's not hard to confirm that that's a solution. Just take that, plug it in, the equation works. Okay. So we can call this our particular solution. We know from a previous example that these are the homogeneous solutions. Namely, those are the solutions to this associated homogeneous equation. And keep in mind, when I say associated, I mean that the left-hand sides are the same. In other words, we're talking about the same L operator. So knowing as we do a particular solution, knowing as we do all of the homogeneous solutions, we know that the complete set of solutions is the sum of them. Particular plus homogeneous. So I think it's worth every student's time to take a few minutes and go back, look at the statement of the similar theorem in Chapter 1. Look at the proof of that similar theorem. Note that both the statement and the proof are very similar. It's very strong similarity between the kinds of equations that we're talking about here versus the kind of equations we were talking about back in Chapter 1. Very strong connections.